Okay, so let's look at another example of for chapter 11. So in this particular example, we have a cross flow heat exchanger and not a counter flow or a parallel flow heat exchanger. So the question says that water flows through a pipe, water flows through a single tube, cross flow heat exchanger. So single tube means it's a single pass, and we have cross flow with no fins. So we know that there are no fins. Now no fins means that your air or the fluid that is flowing over the pipe will be unmixed. And air is used to cool the water running in the tube, which is a mixed flow. And we have to find the overall heat transfer coefficient. And we know what the area of the tube is. We know they've given us the mass flow rate. We know what the inlet temperature of water is. It's at 400 Kelvin and it exits at 340 Kelvin. And the mean temperature for us to calculate the heat capacity is 370 Kelvin. So the heat capacity at 370 Kelvin is 4.214 kilojoule per kg Kelvin. And for air, the mass flow rate is 2 kgs per second, and uh, air is initially flowing at the inlet. The air is at a temperature of 290 Kelvin, and its specific heat is 1.007 kilojoule per kg Kelvin. Now, the first thing we have to do in such problems is that we have to calculate uh, the heat capacity rates. That's the uppercase C, which is nothing but the product of mass flow rate times the specific heat capacity of that particular fluid. So the heat capacity rate for the hot fluid, which is water, will be 842.8 watt per Kelvin, and for the cold fluid it will be 2014 watt per Kelvin, because we know the mass flow rates and we know the specific heats. This means that our CH is the minimum has the minimum heat capacity rate, which we will use to calculate our effectiveness or the Q max. So our Q max is equal to C min, which is this value here. So C min is for the water. So, and the maximum temperature difference that can be achieved by water is it will enter at THI, and it will leave at the uh, inlet temperature of the cold fluid. So that is the maximum temperature that can be achieved in any heat exchanger, which gives us a heat transfer rate of 92,664 watts. Now our actual heat transfer coefficient Q is CH, which is this value here, times the temperature difference of water only, the actual temperature difference of water, which is THI minus THO. So THI will be 400 Kelvin, THO will be 340 Kelvin, and this will give us a Q of 50,544 watts. So dividing Q by Q max will get the effectiveness of the heat exchanger, sorry, and the effectiveness will be 0.55. Now we can use this effectiveness to calculate our NTU, which is the number of transfer units. And the formula for number of transfer units is the overall heat transfer coefficient times the area across which heat is being transferred divided by the C min, which is the uh, heat capacity rate, and whichever for the fluid, and whichever is the lower one, we use it in this formula. So now we don't know what is the formula for the number of transfer units, or we have that, or the question does not give us how many number of units were transferred. So we need to find the relation between eta which is the effectiveness, and NTU from table 11.4. Now the table has different relationships, uh, different relations for a parallel flow, for a counter flow, for a baffled heat exchanger, for a cross flow heat exchanger, and for cross flow heat exchangers, you'll have a relation for a single pass and where your semen is unmixed. So for water, and for that case, we'll use for this case, our NTU is minus natural log of 1 plus 1 divided by CR, and CR here is the heat capacity rate ratios. So I'll just define that in a moment, times ln log natural log of 1 minus effectiveness times the CR. Now, I just realized that in the question it was mentioned that water was mixed. So just a correction, that water is unmixed. It is not mixed. It is unmixed. So CR, so we've already calculated the effectiveness, which is 0.55, and our CR is equal to Cmin divided by Cmax, and we get it as 0.42. So we'll substitute these values in this equation here, and we get the value of number of transfer units as 0.981. Then we can use that value to calculate our overall heat transfer rate. Now this is a different approach of calculating the overall heat transfer rate than we did in the previous example. So in the previous example, we calculated the heat transfer coefficients for the two fluids, and then we added the two resistances to calculate the overall heat transfer coefficients. But in this case, we are using the number of transfer units to calculate the heat transfer rate. So we know what Cmin is, we just calculated what NTU is, and we know what the area across which the heat is being transferred, it's given. And on substituting these values here, we get our overall heat transfer coefficient as 20.67. So uh, remember, this is another approach. So whenever you don't have sufficient information uh, to calculate the heat transfer coefficients, or if you are given a, if you have a counter flow or a cross flow heat exchanger, you can calculate the Qmax. Then with after calculating the Qmax, you can calculate the effectiveness and the heat capacity ratios CR, and you can use the relation from the table to calculate your NTU, which will eventually give you a value for your overall heat transfer coefficient. So go through table 11.4 and see how the different relations look like, and that's it.